So this is a forces in equilibrium problem, and I'm emphasizing forces and not torques. And I'll say more about that along the way. Now, this style of problem could have been taught with Newton's laws. It's one of those topics that can fit in multiple units. Sometimes, and maybe even often, this is taught with forces and when you're first introduced to forces. But I choose to put it in the unit on equilibrium. But we're not going to deal with any torques, and I'll say more about that. But what we have here is a mass that is suspended from a cord, and there's a knot of sorts here. And we have cable 1, cable 2, at a 45-degree angle, at a 30-degree angle, and this is some kind of ceiling that's holding the cables. And we're interested in the tension, and it's interesting to note that the tension in these three cables is actually different. I'm also going to say this repeatedly. The length of these cords is inconsequential. We do not care about the lengths of these cords. In fact, if I were to, I'm going to draw a makeshift wall here. If I were to draw this makeshift wall like so, and this still makes the same angle, that makes a 45-degree angle with a vertical, the result would actually still be the same, which is interesting to note. And the same over here. If I were to have this attaching to a wall, and this makes a 30-degree angle with the horizontal right here, I'll illustrate that horizontal for you and turn this into a horizontal line. If my reference point is this horizontal line, it's not letting me grab that. If my reference point is this, oh yeah, okay, interesting, horizontal line right here, then if that angle was 30 degrees, you'd get the same result that we're about to get here. So there are no torques involved, and I will now explain why there are no torques involved. And of course, pause this video at any time and sort of digest this. But why are there no torques? I'm going to put it to you this way. There are no torques because no rigid body like a beam. In other words, there's no point in this diagram when you think about it. There's no point where there's some object that can have multiple forces on it at multiple locations. In fact, we're going to treat this problem as forces located at a particular point, and that point is right here. Okay, so this is going to be all about the forces at a particular point. No rigid body. All right, so now I'm going to draw the forces on this object. Okay, so here's the object, and this force diagram is critically important. So here's the object, which I'm representing as a dot, and that dot is going to be located at this knot right here. Okay, that's sort of the nexus. That's the point where everything happens. That's where the action is. Okay, the first critical step is the technique I recommend is this. Do not draw the angled forces right away like this. Don't go in and draw the angled forces like this. It's not going to do you any good because you're going to draw them with lengths that are not appropriate. You're going to probably draw them like that. Don't draw the angled forces yet. Don't draw the tensions yet. What you're going to draw first are the components of the tension, and more specifically the horizontal components of the tension. And the reason I recommend the horizontal components is you want to try to find two components that you know happen to be equal in this given situation. So these two tensions we know are equal. And just to emphasize that they are components, make them dotted lines. Okay, so these are the horizontal components of the tension. Now I can go in and draw the tensions themselves at the approximate correct angle. So here's my 45-degree angle tension, and these are not cables. I'm not drawing cables, I'm drawing tensions in the cables. So these lengths represent how much tension is in the cable. The lengths do not represent the length of the cable. These are not cables, these are not the lengths. This next force is going to be at a 30-degree angle from the horizontal. And you can see right away, counterintuitively to some, this force here is actually, this force here is less than this force here. The way I like to think about that is this cable is more vertical, so it's bearing more of the vertical weight than this cable. Kind of interesting result. And now I can go in and I can draw the vertical components. The same way we've always drawn components to match a vector. And you're going to have two components side by side here. So there's the ft2y, and now I will draw ft2x, and they are not equal to each other, but they point in the same direction. Okay, and now I finally can draw the downward weight force. Now the downward weight force, since this is an equilibrium, has to equal the sum of those two, so I'm drawing that longer than either of those two. So here is my force diagram, and it's very hard to label with the mouse, so if you can, if I can just point out what each of these forces is to summarize. It would take a long time to type this all or to label it. So this is Ft1, Ft2, mg, the weight. This is Ft1x, Ft2x. This one here is Ft1y, the little one is Ft1y, and the bigger one is Ft2y. Well, I'm going to use my equilibrium conditions even though there are no torques involved, and now I can write some equations and solve. I know that it's still true that the forces left equal the forces right. The sum of the forces in the x direction are essentially constant, or it's in equilibrium in the x direction, I should say. So I'm going to pull out the equations for that. So here's the solution essentially, and I'll go line by line here. So don't rush ahead. You can pause the video. Just let me explain line by line here. So in the horizontal direction, I know that T1x equals T2x. And I can write T1x as T1 times the cosine of 30. T2x I can write as T2 times the cosine of 45. Now, I've got two unknowns, and I know I'm going to substitute later, so right away I'll write this as T1 equals all this stuff. And I know I'll be substituting this in. Okay, let's table this for now. And let's focus on the vertical. In the vertical, it's not that the y components equal each other, it's that the y components sum up to the weight. So in the y, I know that T1y plus T2y equals mg. T1y is T1 times the sine of 30. T2y is T2 times the sine of 45. And the weight, because it was half a kilogram, is 4.9. Now you're going to plug and chug. You're going to take this expression for T1, which is that it's T2 times the cosine of 45 over the cosine of 30. You're going to put this whole expression in right here for T1. But don't forget about this sine of 30. After you do this ratio, you're going to have cosine 45 over cosine 30 times the sine of 30. You plug, you chug, you solve, you get 4.39 newtons and 3.59 newtons. Now you can check that very simply by just going back to this original diagram, and you can ask yourself, you can say, sorry about these arrows, it's getting interesting. Arrows. Okay, you can ask yourself, if I take this known component, which is 4.39 right here, 4.39 is this vector, times the cosine of 45, you get this, and does that equal 3.59 times the cosine of 30? They do. Try it. And you can take 4.39 times the sine of 45 plus 3.59 times the sine of 30, add them together, do they equal the weight of 4.9 newtons? And they will. Now, you can try this problem on your own. I would pause the video and try this. Find the tension in the two cables. Here's some arbitrary mass. I don't know what that is, but it's 11 kilograms, and you've got two cables. 45 degrees, 60 degrees. Try to find the tension in the two cables. Try it right now. Pause the video. So here's the force diagram. Note the two equal x components, the two y components that add up to the weight. You plug, you chug, you solve, and you should get 55.8 newtons. And you should get 78.9 newtons. And you can check, does ft1y plus ft2y equal mg? Does ft1x equal ft2x?